Welcome to qnawire.
Okay, so in this case, you have a real life scenario where you have a car moving due east or to the right with a certain velocity v1 I, and the car is mass m. And then you have a similar car going north with a certain velocity v2 I. So you're told that these cars collide somewhere on the intersection here, and then after the collision, the cars stick together and they both travel north of east at an angle of 55 degrees with a certain velocity that you're not given, v final. And the question says this driver claims that he was going slower than 35 miles per hour, which is also 15.6 meters per second. And you're told that this car was moving at 13 meters per second. So you want to prove whether or not this driver was actually below the speed limit of 35. So in this case, you have a two-dimensional problem. You have x motion and y motion. And since momentum is a vector, you're always going to have to deal with the components, because you cannot just use these numbers and calculate these things in assuming one direction. So you have two-directional motion. So we have conservation of momentum in both directions. So if we look at the x direction, for example, the initial momentum should be equal to the final momentum always. And this is just in the x direction to start with. So the only car that's moving in the x is the first one here. So this would be mv1i plus 0, because this has no component in the x. It should be equal to the combined mass of the two cars. But now this is moving in an angle, so it has an x component here. So the component is just given by, if you remember, by the, so you have to resolve this direction into the x. So if you remember your trigonometry, if you have your hypotenuse here, which is the final velocity, and you want to find this adjacent side here, the only way you can do that is to use a cosine. So this will actually be just the cosine of 55. Because the cosine of this angle is the adjacent over the hypotenuse, which will give you the adjacent here. And then, so now times again its final velocity, Vf, because we're getting the component of this final velocity here. So now you have an expression for V1i once you divide by the masses here. So V1i is actually equal to 2 cosine of 55 times V final. And now we want to do the same for the other direction. And again, this has 0 component in the y, so the only car that's moving is the second one. So this will have v2i is now equal to, again, the y component of this velocity, which is going to be plus the combined mass. So this is 2m. But now this is the sine, because we're now looking at the opposite side here. So this is sine of 55 times the final velocity. And again, you remove those masses, so you find a similar expression for the y velocity here. That is going to be 2 sine of 55 times the final velocity. So so you already have the initial velocity here, so you can go ahead and just find v final, but it's slightly more straightforward to say divide these two equations here, because now we've converted all these equations into some scalar quantities. So now if you were to divide, say, V2I over V1I, you find that, so if you take this, divide by this, you have a sine over a cosine, which is the tangent, and these things cancel and that cancels. So this is actually equal to the tangent of 55. So now we know what the tangent of 55 is. We know what the initial velocity is. So we can go ahead and just compute directly what V2I is going to be, and we find that V2I is actually 18.57 meters per second. So if you compare it with the speed limit, you find that this was actually much faster than what the speed limit was. So essentially, if this driver says they were below the speed limit, they would be a lie, because the math shows that there's no way that could have happened.